Hi everyone, welcome to Netgate Chemistry. So the last topic which we studied was orbital selection for overlapping, and today we are going to study the topic relation between percentage S character, percentage P character, the angle, and I. I is your hybridization index. So if we take an S orbital and one P orbital, I have told you that both of them are going to exchange their characters with each other, forming sp-sp hybridized orbitals. So these types of mixings can be ideal or can be non-ideal. We'll discuss about the ideal and non-ideal mixings later on. So I don't know that this sp mixing is ideal or non-ideal, but one thing I can tell you that both have S and P characters, but right now percentage cannot be known. Okay, next is your hybridization index, represented by small I. Hybridization index is nothing but indirect measure of hybridization. So in terms of formula, I is equals to P upon S. P is your P character, S is your S character. Both are in fraction, or you can say decimal. Both are same. So in terms of angle, cos theta is equals to minus 1 upon I. This is another formula. From 1 and 2, cos theta is equals to minus S upon P. See, S and P character is always equals to 1, or we can say percentage S plus percentage P character after mixing is always equals to 100%. This is in terms of percentage, this is in terms of fraction. So if we use this formula here, we can get two more formulas. Cos theta is equals to S upon S minus 1, and cos theta is equals to P minus 1 upon P. All of these are derived from each other. Now we'll get to know about the ideal and non-ideal mixing. Basically, the nature of hybridization could be ideal or non-ideal. In which case it is ideal and in which case it is non-ideal, we'll see to it. So nature of hybridization. It could be taken into three categories in terms of I, that is hybridization index. If I is equals to minus infinity, then this is the case of no hybridization. If I is any integer, for example 1, 2, 3, so on. This is the case of ideal hybridization. If I is your fraction, for example, 1.2, 2.4, 3.8, fraction or decimal you can say, then this is your non-ideal hybridization. So these are the factors on which you can divide nature of hybridization. If I is equals to minus infinity, it is the orbitals are not hybridized. If I is any integer, then it is ideal hybridization. If it is fraction or decimal, it is non-ideal hybridization. Now, this was the nature of hybridization. Next is the type. Type is defined with the help of hybridization index. Type will be of the form sp to the power I. If I is equals to 1, then it is sp hybridized. I is equals to 2, then it is sp2 hybridized. I is equals to 1.1, then it is sp to the power 1.1 hybridized. So this is your non-ideal hybridization, and these are your ideal hybridization. Okay, so inside the types you can define the nature of hybridization. Type could be sp, sp2, sp to the power something, but inside this type you can also define some are non-ideal while some are ideal in nature. So if we look at some of the examples, for example, our carbon dioxide, it has angle of 180 degree. So I will be equal to minus 1 upon cos theta, or you can say cos 180 degree. So cos 180 degrees minus 1. So minus 1 upon minus 1 will be cancelled out. We get I is equals to 1, which is an integer. So CO2 is the case of your ideal mixing. Next, you can take the example of NO2. This angle is 135 degrees. If we take out I, that will be minus 1 upon cos theta, that is 135 degree. Cos 135 comes out to be minus 1 by root 2. Okay, this goes up root 2. Value of root 2 is 1.414. So this is fraction or decimal. So this is the case of your non-ideal mixing. This way you can find out which one is ideal mixing and which one is non-ideal mixing in case of hybridization. If you want to determine the percentage S character and you know the angle, then you can calculate percentage S character by this formula. Okay, don't take percentage. Take in terms of fraction. S will be equals to cos theta upon cos theta minus 1. If you know the angle, you can easily calculate S character in the bonds. All of these formulas are applicable when lone pair is not present. If lone pair is present, then how to calculate percentage S character? Then percentage S character in lone pair will be equal to 100 minus sigma percentage S character in the bonds upon number of lone pairs. How to apply these formulas? we'll take an example and then we'll solve it. For example, we have a molecule AB3. Each bond angle is 120 degrees. Here lone pair is not present, so we'll apply this formula. So S character will be equal to cos 120 degree upon cos 120 degree minus 1. Cos 120 degrees minus 1 by 2 upon minus 1 by 2 minus 1. This comes out to be, next line, minus 1 by 2 upon, take the LCM, 2 minus 1 minus 2, take the cancel out, minus 1 upon minus 3, 1 by 3, that is 0.33. S character is 0.33 or percentage S character is 33.33%, you can say. Okay. This is first example. For second example, I'm taking A, B, and C, and there are two lone pairs here. Okay, this is a molecule. There are two lone pairs. This is bond AB. Suppose this is also B. The angle is theta here, and this bond, this AB bond, contains 15% of the S character. This is given in the question. So this is also the same bond, so this will also contain 15% of your S character. So how to calculate percentage S character in these lone pairs? So what we'll do, we'll apply this formula. So percentage S character will be equals to 100 minus, here the percentage S character is 15%, plus, because it was sigma, sigma means plus, this bond had 15% S character and this bond had 15% S character, upon number of lone pairs. There are two number of lone pairs. After solving, 100 minus 30, 100 minus 30 is 70, 70 by 2 is 35, 35%. Each lone pair will be having 35% of the S character. So this is how you calculate percentage S character in the bonds and also in the lone pairs. So all these formulas are very important to calculate percentage S character. In the next video, we'll discuss about how percentage S character is used to study the different aspects like the angle, how it is related to the angle, and how it is related to the bond length, bond strength, electronegativity, and so on. So that's it for this video. Thank you so much for watching.